Okay, this video is about quantizing filter coefficients because we talked about in class, sometimes you're going to want to implement a filter using fixed point math and you only have a certain number of bits to represent all the numbers for those calculations. Okay, so let's draw a picture here of the rectangle that represents a number. Okay, so if I have a number like 21.68317, okay, I need to allocate a certain number of bits for number one, the sign. This is a plus number. All right, so maybe you'd have a sign bit like you do in 2's complement. And then I have to represent the integer part. Okay, so if I was going to do that, I would need, how many bits would it take to represent 21, positive number 21? Well, 4 bits to the fourth is 16, so 4 bits is not enough. It would take 5 bits to represent the number 21. So I'd have 5 bits here, 1 bit for the sign bit, and then if I was doing 16 bits to represent this number, the other remaining bits could be for the decimal part. Okay, so I'd represent this particular number in decimal for the decimal part. Okay, so that's the idea, that you're always going to have one bit for the sign bit, a certain number of bits for the integer part of a number, and a certain number of bits for the decimal part of the number. All right, so included with the ProAcus book is some MATLAB code that lets you play around with quantizing any particular number. All right, so first thing I'm going to do, make up a number. All right, I made up a negative number. It doesn't really matter. The thing to remember is you always have to have a bit, 1 bit allocated for the sign. Okay, so there's the number x. I put this into this Q coefficient function. Okay, scratch that E there. The way he runs it in the ProAcus book is if you want 16 bits, you always remember you have 1 bit for the sign bit, so the precision that you're looking at is n minus 1. Okay, so 16 minus 1, we put the 15 here. All right, and then this particular MATLAB command puts out the truncated or the quantized number. It also tells you how many bits are for the integer part and how many bits are for the decimal part. Okay, so if I take a look at this number with 16 bits, you notice the original number had some decimal points out here, and then we end up with zeros because this is quantized to 16 bits. All right, it takes 3 bits for the integer part. Okay, does that make sense to us? Well, 5, it takes 3 bits to represent 5. 2 bits is not enough. The most 2 bits can do is 4. All right. And so there we go. Then the decimal portion is just 15 minus 3, which is 12, because we have 1 bit for the sign bit. Okay, so if you did this to 8 bits, what would it turn out to be? Well, you still need the 3 bits for the integer part, and you just have less, fewer bits for the decimal part. Okay, one more example. Take another number. This time the integer part's bigger. Okay, so in MATLAB here, e to the 2, so it's scientific notation, 600 minus 639.394912, so forth. If I plug this in here and go to 16 bits, okay, it's going to take me 10 bits to represent the 639 part. Okay. 10 bits is the integer part of that. And then, so that leaves me the 5 remaining bits for the decimal part. Okay, so, if I went with 11 bits for representing this number, that's the minimum number, right? That's the fewest I can use to represent this number and still capture the sign, because I have 1 bit for the sign, and then it takes me 10 bits for the integer part. Okay, so that's what you need to know. We're going to look at what happens when you quantize coefficients. This tells you exactly how that's done. You notice that, as you move from smaller numbers, more bits of quantization, fewer bits of quantization, you get more and more zeros in the decimal part. Okay, so I think you know what's going on with this, and what we're going to do is we're going to quantize coefficients of filters and then look at how that affects the frequency response.